Hello, good morning, everyone. My name is Marcello, and together with Simone, we're here to talk about something that should keep you up at night, but probably doesn't yet. We're going to talk about what happens when the containers running on your IoT fleet aren't really yours. So, quick intro, I will cover the scary stuff and the tooling landscape. Simone will then show you how to actually fix it with Eclipse Kura. We will split the talk in half. Like a good container image, we believe in separation of concerns. So let's set the stage right now. There are roughly 3 connected IoT devices for every human being on the planet right now. 3 devices per person, and that number is growing double digits year over year. And increasingly, these devices run containerized workloads. Your industrial gateways, your smart meters, your medical equipment, they're all doing Docker pulls some way, some day during the week. Now, here's the message that I want you to carry throughout this talk. Every one of those devices is a deployment target. Every one of them pulls software from somewhere. And every one of them trusts that what it pulls is really genuine. That's a lot of trust. But the question is that trust earned, or is it just assumed? Because assumed trust at this scale isn't optimism, it's a vulnerability. So, would you eat a sandwich from a stranger's backpack? Well, probably not, but that's what your devices are currently doing in the field right now. Ask yourself these questions. If you really can't answer them with confidence, then, well, this talk is really for you. Let me give you some real stories, and this time they're all specifically about container images. The first one is fairly decent, is the 3V Docker Hub compromise. Attacker stole CI/CD credentials from the Aqua security team and pushed malicious versions of the official 3V security scanner online. Some version tags and the latest tag contained an info stealer, which was exfiltrating cloud credentials, SSH keys, Docker configs from every CI that pulled that image. The irony is that the tool that was meant to protect you, your supply chain, became the attack vector. Next, we have the Dero CryptoMiner worm. This was a worm-like campaign that exploited Docker APIs to deploy crypto miners containers across thousands of hosts. Each infected container then scanned for new victims automatically, and the containers were using names like Nginx on cloud to blend in. No signatures were checked in this case. Then we have the execute backdoor, which is still persisting on Docker Hub, also currently now. After the backdoor was discovered, researchers found out that hundreds of Docker Hub images still contain the compromised library in some of their layers. Every single of these would have been caught or prevented by proper container image signing and verification. So let's formalize a bit the threat model. There are 5 main ways unsigned containers can ruin your day. The first one is the registry compromise. Someone gets access, for example, by stealing your credentials, and pushes a bad image. Then we have man-in-the-middle attacks. It's less likely with TLS, but if it happens, an unsigned image gives you 0 way of detecting it. Then malicious code can be injected at build time. If the signing keys live in the same pipelines, then every signed image can lie. Then we have the tag mutability, because latest is just a promise, it's not a guarantee. And of course, the insider threat. Without multi-party signing, there's no way to produce audit trails, and no one can notice them. Signing itself doesn't solve all of these alone, but without it, you can't solve any of these issues. So what's the solution? As you may have guessed already, sign and verify container images. You sign your container images when you build them, you store the signatures, and before your IoT device runs anything, it checks the signature, and if it doesn't verify, the image doesn't run, period. Sounds simple enough, but the devil's in the details, as always. Now, let's look at the available tools to build this chain of trust. Currently, there are 3 main tools and technologies that try to solve this problem. For each of one, I'll give you a brief explanation and then highlight the main pain points and limitations. The first one, it's Docker Content Trust, or DCT. It's built right into the Docker engine and is based on the Upgrade Framework, or TOF in short. And the main protagonist here is a Notary server for key management. So it implements the Upgrade Framework, so keys are arranged in a hierarchical model. Images are signed by tag, and when uploaded, if an unsigned image already exists, they will coexist together. When pulling, you will pull the signed or the unsigned version based on whether you have the feature flag enabled or not. DCT binds to the push, build, create, pull, and run commands. This means that when the feature is enabled, the signature is always applied or verified in those stages. Here I have an example for signing and verifying a tag. Steps are really simple. You just create a key pair or import a signing key, then upload the key to the Notary server, and the signing of the tag is then straightforward and can be done with a single command. Verifying a tag is as simple as enabling DCT with its environment variable before pulling the image. The signing procedure here is the complicated version, let's say. If you already imported the key, you can simply enable the feature with this flag here and push. It will do the signing like automatically. You flip one environment variable and suddenly every push signs and every pull verifies. One variable to rule them all. Almost too easy, right? And yeah, spoiler, it is. So here's the fine print. DCT only supports one signature per image. If you need both your security team and the CI to sign, then yeah, good luck. There's no provenance or attestation metadata support, and the complexity is hidden in the Notary server, which you must maintain. There's key management overhead. If the target key is stolen, an attacker can sign a malicious digest. And yeah, but to be fair, there exists a key revocation mechanism. Docker officially announced the retirement of DCT. Since last September, if I'm not wrong, you can't enable it on new registries anymore. So if DCT was a pioneer, it taught the industry that container signing matters, but now it's now like the fax machine of container security. It worked, it was important, and it's time to let it go. Here's a little meme from. Next, we have Notary v2, also known by its CLI tool notation. It's the CNCF-backed successor to Notary v1, and it fixes a lot of pain points. The objective here was to develop a framework for signature verification that you can use to identify that an image that you pull from your private on-premise registry is the same as the one that you can find on Docker Hub, for example. It's OCI native, meaning that signatures are like any other OCI artifacts, and are stored right alongside the images in an OCI compatible registry. This means an easy integration with existing registries. An OCI artifact can be anything, not just container images, and it supports, very importantly, multiple signatures on the same image. So here's a quick example on how it works. For signing an image, you will build and push the image as usual to your OCI registry. Then you set up the keys and certificates and then simply sign the image. The signature command also uploads the signature artifact. This shown here is the tutorial way, but the tool is highly customizable. For example, you can customize it to consume keys from your key management system. For the verification process, you will need to import the certificates into your own trust store. Then an important part is to create a trust policy, like the one that you see here. With the policy, you can specify trusted identities that sign the artifacts and the level of signature verification to use. It can be strict, permissive, skip, or audit. The verification level dictates which verifications to enforce, like the authenticity, timestamping, and integrity, and so on. Then you can simply import the policy and issue the verify command. Think as a notary, as the industry saying, okay, we've heard all of your complaints about DCT, here's a do-over. And that's a pretty good do-over. But there's always a but. We have some limitation also in this tool here. Notation, first of all, doesn't come with its own certificate authority. So you will need to bring your own PKI. If you're a large enterprise with a dedicated security team, that's okay. But for the rest of us mortals, it's not a trivial task. Especially for a CI runner that spins up and dies in 30 seconds, managing long-lived keys is a real operational issue. Currently, but they are working on it, it doesn't natively support attestations, so you can't attach SBOM or provenance metadata to it. And there's no public transparency log by default. Signatures live in your registry and nowhere else. There's no global auditability, but you could wire it up with record, which is a public transparency log, but it's not the default way. It's only compatible with Docker and not Podman. But yeah, overall, it's a really solid tool, and it's standard-driven. But what if I told you that there's another tool that looked all of these limitations and said, yeah, hold my beer. Next, we have Sigstore Cosign. It's part of the Sigstore project, and Cosign basically looked at every limitation that we had in DCT and notation and decided to solve all of them at once. What is Cosign? It's an agglomerate of different technologies to sign and verify artifacts. It provides, and this is crucial, identity-based signing instead of key-based signing. As we've seen, distributing keys can be challenging to do securely, and Cosign allows for keyless signing. Then you authenticate with your identity provider. It can be GitHub, Google, or whatever, and Cosign gets an ephemeral certificate from Fulcio. This is a short-lived certificate tied to your identity, used for exactly one signing operation, and then discarded. So you don't have to worry about long-lived keys anymore. Every signature is recorded in record, which is a public transparency log. This means anyone can audit who signed what. You can think of it as a blockchain, except this time it's useful. It supports rich attestations, and it features a broad key management system support if you don't plan to go keyless. In short, DCT was like the flip phone, notation was the early smartphone, and Cosign is probably the Apple device that you have in your pocket right now. You had problems, I've got solutions, plural. Now, let's look into more detail the sign and the verification procedures. I think those are quite interesting. I'm a computer science nerd, I like algorithms. There are three main actors. We have the OIDC provider, Fulcio, and Record. Fulcio is the Sigstore's CA that can issue short-lived certificates. Fulcio checks your identity and bounds the generated certificate to your public key. Every activity like this is then logged into Record. This is the client signer flow. It starts by retrieving the OIDC authentication token at line 2. And this token contains two relevant fields, the issuer and the subject. Then at line 3, we generate a key pair and a corresponding certificate signing request. With this information, the client submits a certificate, the certificate signing request to Fulcio, which will return a certificate signed with its own CA key. For the Fulcio request, a challenge is attached, as you can see at line 4. This challenge is used at server side to verify that the request arises from the claimed identity. The certificate returned on line 5 will contain the same subject and issuer field as the OIDC token. And the client then signs the artifact at line 6, and then with the generated private key that he generated before. And then he discards the key and submits the signature to Record. And then he will simply push the artifact to the OCI registry. The algorithm 2 is the Fulcio algorithm, shows the Fulcio server flow. When a request arrives, it will first verify that the OIDC token is legit. The important part is at line 4. The challenge is decrypted with the identity public key. If the request is legit, then the decrypted challenge will match the token subject. Full SEO is sure in this way that the challenge was issued by the requester. So let's move to the verifier part. A client first ensures that the trusted keys are fresh by updating their CA at line 2. Then, with an updated root of trust, the first check at line 5 ensures that the identity claim was correctly verified by the identity log. Line 7 checks that the signature provided matches the content of the signed artifact using record. Final checks are just for verifying that the signature was created during the time validity window of that certificate. Everything is hidden in the Cosign verify command, so it's very simple to use. And yeah, this one that I showed you is the keyless flow, which is the most interesting one. But you can configure Cosign to leverage your own PKI and key management system. So now wrapping everything up, this is a slide to photograph. We have that, Docker DCT is now retired. Notary V2 is not yet released. It's still in alpha release, I believe. Sigstore Cosign instead is the one that is released. The two newest tools, Notary and Cosign, are using OCI registries instead of the Notary server, and they both support multi-signatures. Keyless signing is just supported by now just by Cosign, and attestation is fully natively supporting Sigstore Cosign, whereas in Notary V2 it's not in the default process. We can say that, but among the three tools, Cosign is the most mature one. Okay, now here's the part where we remember that this is an IoT-specific talk, right? Because signing in a CI pipeline is pretty easy. You can do everything just 5 lines of YAML code. But yeah, verifying on the edge, that's the real challenge. How do you distribute verification keys to 10,000 gateways scattered across the globe? If you choose, for example, keyless signing with Cosign, verification needs to reach record and full SEO. So that's fine in the cloud, it's not really in the field. Here is where Eclipse Kura comes into play, and now I will hand off to Simone, which is now going to explain how to solve these challenges.
Yeah, thank you, Marcello. Hi, everyone. We talk about the IoT stuff. So, what is Eclipse Kura, and we're gonna answer mainly 4 questions. The first one is how we handle the container security in the edge IoT world. Is there a tool that could help us? And yes, here we are for this. And why Kura can help us, and why you should trust us in this process. Yeah, mainly we are trying to resolve the edge security dilemma because we're starting from a device. Let's think about the single piece, which already has kind of problems like the limited resources on the chips, the internet connectivity, which could be an issue, complex key management, and we're gonna not only multiplying these problems on hundreds, on thousands of devices spread around the world, but we're fighting around different environments because our devices can be deployed everywhere, unreliable or even absent network connectivity. And we usually work in a cloud-based system management where we want to upload thousands or deploy thousands of containers or codes everywhere in the world with a one-shot approach, let's say. So when we started working on how we can, as an IoT framework like Kura, manage this stuff, we think that the best way is to manage a scalable model. So something that can be introduced and it can be provided inside the change from cloud to devices on the edge, trying to resolve or at least find to compromise about the problems that we talk about. So a lightweight modem that must ensure for us security. So we think that the verification at the really end of the chain is the best because we can deploy once and have different devices that checks on their own the security, scalability, exactly, because we want to work from the cloud, and zero trust by design. So if we don't trust anyone between the deploy and the execution of the code, we are sure that when we do the check at the very last mile, we're there, and we're sure that no one is inside the chain. So the solution, yes, it's us. It can be Kura. And what is Kura? Kura is the Eclipse IoT framework for the IoT devices, and allows you to have a complete management of the devices. So from networking to firewall, user access management, and of course, container lifecycle management. So you can use Kura to, let's say, monitorize the engine that you have on your device, and let's say, catch the events, pull, start, verify containers, etc. One of the main features of Kura is the integration in the cloud-to-device deploy chain, because we have services like the Kura Cloud Connectors that allows you to connect the devices to your favorite and the best cloud provider that fits your need. For example, let me do a sort of presentation of Kapua, which is like the counterpart of Kura for managing the cloud part of the chain. So the real question is, how do we decide to secure containers on Kura devices? And we started from researching the state-of-the-art tools, like the ones that Marcello presented, because we already had the, let's say, the management of the containers, but we wanted to increase another security layer on top of it to manage also the security. The key issues that we find is that incompatible formats, because each tool wants to do the stuff in its own way. So it was a very hard process to, let's say, make those different actors work together. Weak enforcement, because some of these tools can be just disabled by a command line interface command. And they cannot rely on vendor signatures, because we should be bound to one tool, and maybe it will be difficult to move to someone else in the future. So our goal was to create a strong and reliable enforcement. We had lots of meetings, and we noticed that we are developers, so we can develop something. And we decided to develop our own signature enforcers on Kura. So we wanted extensible APIs that were totally agnostic in respect of the backends, the architecture, the OS that were running on the devices, and that gives you full control of the all the events that the engine could trigger, and it was easy to add formats. So the simple idea that we start is, if it's not safe for whatever reason, it won't run on our devices. So we're gonna move on the actors that works on this game. The first is the container orchestration service, which is the core service about for managing the engine. We said, okay, we already had, in this slide you see the configuration UI that you can use. The first two properties were already there, so you can enable the supervisor, because you have to imagine this service like a supervisor that monitors constantly all the work of the engine. So even if you run something from the command line interface, the event is catch, and of course the engine that you want to monitor. We added this second layer, so the allow list enforcement, which starts from a simple idea. We have a constant monitoring of the engine. We can use the digests to enforce to be sure that the images that are running are the ones that we want. So someone could add a list of digests, like the one in the example here, and he is sure that only the containers starting from generated from that specific image are allowed to run on the system. So we have an agnostic, so we are already, let's say, checking one of the goals that we want, because it's agnostic, because the digest is an intrinsic property of the image. We have an immediate reaction, because if the digest is not verified and you don't match it, you don't run the container. Connectivity independent, because it's something that could be done even offline, because once you put the digest in the configuration of the supervisor, you have always the check, and you have complete control. But we're lacking the first thing that we said in the second part of this presentation. We want to work on the edge in a one-shot way, in a cloud system based. So do I have to put the digest every time to all of my devices? No, we don't want to do that. And so Kura, in the Kura team, we decided to develop the container signature validation service, which is a set of APIs that you can see here that allows you to build your own tool on top of the Kura services. So you have generic parameters like the image name to verify, the image reference, the trust anchor, transparency log enable, nothing that is bound to a specific tool. And the concept that we want to enforce is that we have engine agnostic, backend agnostic, tool agnostic, but the process that we want to achieve is that you pull once the image, you verify once the image, and then you can run whatever time you want. So the fun part that I'm already spoiling is that when you develop an implementation of these APIs, Kura automatically, once it verifies an image, added the digest to the enforcer that we talked about previously. So you have already to verify once with these APIs, and then you can run whatever number of containers you want on the system. So, exactly. You pull the image first, Kura verifies the signature. If the verification is successful, we move the digest and we store it, we cache it automatically, and then you run the container. So think about a situation when you deploy your devices, you deploy the bundle which implements these APIs, and then you can decide to deploy whatever container you want, whatever image you want, because you know that Kura, on the very last mile of the chain, will check in each device if the container that you're running is the one that you want. So we reach our goal of the zero manual intervention in the process. But we say, okay, we are monitoring the command line interface Docker that are running, but Kura lets you add another layer, which is the container instance, which is the abstraction that we made on Kura for containers. So this is a piece of the configuration that you may add, but starting from the image name and the image tag, you can start configuring the, whatever properties you want of the Docker. So connectivity, GPU usage, memory usage, CPU usage, whatever you want. We're not here to present the container instance feature, but give it a check because it's a very strong and very powerful service. We want to talk about the integration with the APIs that we showed you just a couple of minutes ago. Here there are a couple of pieces of the configuration, so image name, for example, and tag, which could be the latest. So if I want to run the latest image, do I have each time to add the digest to the enforcement? No, because Kura will check against the latest version of the image that you got. Then we got, for example, authentication registry, if you want to use private registry to pull your images. And then trust anchor, so the public key or the certificate that you want to use to verify your images. You don't want to use the verification by Kura. You want to put your the digest of the image by yourself. You're free to use it because we provide also this property. So if you want to spend a lot of time, we doesn't deny you the pleasure. But let's talk now about how to wrap up all that what we said. So starting from a container creation on a start event, again, both from a Kura container instance or from the command line interface, because as we said, we wanted to full control of the device. Kura checks immediately if the image digest from which the container has started is in the allow list enforcement. If it's, then you are allowed to run and Kura won't stop it. But if it's not verified, we move. Is a trust anchor available in the configuration of container instance, which could be deployed with the playbook for all the devices that you got on the environments that you work on? No, sorry, we have to deny you, we have to close the door, you're not verified, we're not sure, and then we said, if it's not safe, we won't run it. While if there's a trust anchor available, yes, we move to the signature verification. So Kura will check if there are one or more implementation of those APIs on the system, and even if one of these implementation verifies the image, says, okay, whatever, it's allowed. You can run, we add your digest, the image digest, to our stored cache list of image digest, and you can run whatever container you want, because it's allowed. Small notice, each time that you run a container, we give another round of verification because we want to be sure. The image is not verified, you won't be allowed to run the container. So there is let's say, an immediate denial of running. This stuff works even if you activate, if you enable the verification also when the container is already starting. Because, for example, you already pull your images, you want to implement your enforcer later in the process, no worry, you enable the low list enforcement, that all the containers that are already running will be checked again. So, it's an open source tool, so as you always, as we always do, we want you to implement your own tool, because we are happy if someone uses it and if wants to contribute to the project. So, if you imagine to have the container signature verification service as a property there, you can develop your own tool. If you want to use Notary, you want to use Cosign, you want to develop your own custom verification, you're free to do it. So if you want to contribute, please just do it, because we're happy to have your contribution. Last thing, we want to show you a real case scenario, because there is an integration, we develop an integration as ESF and container signature verification. So what is ESF? In Eurotech, we have a commercial enterprise-ready version of Eclipse Kura, so we build our own framework on top of Kura, and is, let's say, a version which is highly focused on security. For example, in Eurotech, with the integration of our hardware, our Linux team, and the ESF team, we built on top of Kura devices. We get the 62443 cybersecurity certification. But it's not only a result that we did with the ESF, but we cannot do it if we don't have some foundation like Kura, because Kura provided a lot of security APIs, security-related APIs that let us build a framework which is focused on security. And the signature verification API is an example to increase even more these layers of security, because the 62443 cybersecurity certification is already there, but we got lots of customers that wanted to use a container. We was to deploy containers around the world, but they see a rising number of attacks, of cybersecurity attacks. So they ask us, what can we do to secure and be sure that the containers are verified? And so we decided to create our own implementation of the signature verification APIs. So we decided to take we choose as tool the signature Cosign, because it was the one that best fits our need, but we could choose also Notary, DCT. We could also develop our own custom verification service. And so we were able to build an entire secured framework. Because, for example, if you think that you have an Eurotech device with the ESF on it, you have the complete management, you have the certification, you can use it in your different environments, because we provide you also an implementation of the signature verification APIs. And so from the cloud, you can manage a lot, hundreds, thousands of devices in different environments, industrial, transportation, energy, and so on, sure that we achieve what we start with the goal at the beginning. So security, because ESF is a secure framework, automation, because we can connect through the Kura APIs to the cloud, and flexibility, because you can do it just once, so you pull once and you verify each time. And that's what we did. So just some conclusion. We have tackled all this stuff in this presentation. Yeah. Thank you. If you have some questions, we're here.
you.